for this evening is Dr. John Davis, whose presentation is entitled Missions to Near-Earth Asteroids. Our next Zoom webinar is on the 16th of November, when our speaker will be Duncan Lunnan, whose presentation is entitled Incoming Asteroid. Also, please remember we have a SLU workshop on the 23rd of November with Pete Williamson. So, I mean, I will be sending out the link for that, but it's just to remember you to put it in your diary. Right, so there's somebody else wanting admitted.
Okay,
right.
Okay, shall I just share my screen now then, Amanda?
Aye, so if we all mute ourselves and then...
Oops.
It doesn't appear to be working. You seeing the slideshow? Hasn't started yet, has it? Oh, there we go. That's better.
Aye.
You seeing the opening slide okay now, folks?
Yes, that's fine.
Okay.
Yes.
Right.
Yes.
So if I want to mute then, or either that be quiet. And we're just sort of starting off the space news and the way that it was done until recently, just something that's happened on this day. So on the 2nd of November, the 100-inch Hooker telescope located on Mount Wilson Observatory achieved first light on the 2nd of November back in 1917. And it was the world's largest telescope from 1917 to 1949. The picture on the top right shows the 100-inch mirror being carted up the mountain. I don't know if you can see it all that clearly, but it just seems to be wrapped in a Hessian sheet. If anything had happened to that, it got marked on the way up, that would have been a bit of a horror show. It was used by Edwin Hubble to make observations from which he produced two of the fundamental results which changed the scientific view of the universe. Using observations he made in 1922 and 1923, Hubble was able to prove that the universe extends beyond the Milky Way galaxy and that several nebulae were actually millions of light years away. He then showed that the universe was expanding, as we all know, with the Hubble constant. When two neutron stars smashed into each other about 130 million light years from Earth, the universe lit up. The collision between some of the densest objects in the cosmos produced gravitational waves and a spattering of fireworks on August the 17th, 2017. Dozens of telescopes on Earth captured the rare merger across different wavelengths from the electromagnetic spectrum. First, there came a burst of highly energetic gamma rays, followed by bursts of light and UV, radio and infrared signals. About 9 days after the collision, NASA's Chandra Observatory picked up an X-ray signal. According to our current understanding of neutron stars, that signal should have faded away by now. But in a new study published last Monday in the journal Monthly Notices of the Royal Astronomical Society, researchers have studied the neutron star and neutron star impact and discovered that 1,000 days later, the X-ray signal was still detectable. Eleonora Trocha, an astrophysicist at NASA's Goddard Space Flight Center, said, "We really don't know what to expect from this point forward because all our models were predicting no X-rays." Just letting somebody in. This was the first neutron star merger detected by all three gravitational wave observatories stationed on Earth. The triad observatories were able to triangulate the position of the merger moments after it happened, allowing researchers to turn their telescopes to space and get a good look at the event. Because we haven't seen terribly many neutron star collisions, scientists have had to rely on models to predict the aftermath. For the most part, the models lined up with what was detected. When two neutron stars collide, they release a jet of gamma rays and a huge blast of bright gas known as a kilonova. These events are transient. We see them for a few days or weeks and then they disappear. That was the case with this GW 1708-17. But Chandra, NASA's X-ray observatory, was still detecting X-rays at the location when it focused on the merger in February, 2.5 years after it had flared into life. The latest measurements show the signal has faded, but the spectre of an X-ray burst is still visible, and it's a little brighter than models predicted. Why are these X-rays still visible? That's a puzzle the researchers are still trying to solve. Astronomers will turn the telescopes back to GW17 in December, presenting another opportunity to unravel the mystery in the merger and work out what needs to be done to refine the model. These pictures are just pictures from Chandra because they're pretty. They don't really have much to do with the story. Somebody's still unmuted, so I'm not sure. Slight noises coming through. And here's some interesting images of an oddly shaped crater on the moon. Ryder crater is oblong, about 13 by 17 kilometers, with a distinctive slump on its eastern side. And it's located in the South Pole Aitken Basin, which at 2,500 kilometers in diameter is the largest and possibly oldest basin on the moon. Because of its odd shape, some question whether Ryder is actually two craters or one. This distinctive landform could have been formed when an impactor struck the surface at a grazing angle, or when an asteroid split in two just before impact. However, there is another factor at play here. Ryder crater formed on a steep ridge, and this kind of uneven terrain is often responsible for asymmetric craters. The steep ridge upon which Ryder formed is in the degraded rim of an older crater that's around 70 kilometers across, with a vertical drop of over 3,000 meters from its rim to its floor. Just in case it's not clear, that's Ryder right in the middle there. Even this older crater may have been affected by the uneven terrain on which it's formed. Its eastern rim appears to be formed on a topographical high, perhaps related to the SPA basin, leaving it well above its western rim. It seems the impact that formed Ryder crater struck the very highest point in the older crater's rim. And in this case, it's not hard to imagine that the final shape Ryder crater was strongly affected by its lucky encounter with the extra steep slope. The high point of Ryder's rim is about 1,500 meters higher than the low point of its rim. Ryder crater was named after Graham Ryder, a lunar scientist who worked at the Lunar and Planetary Institute and the NASA Johnson Space Center, unraveling the secrets of lunar geology through detailed analysis of Apollo samples. Given his unique and important contributions to lunar science, it's fitting that such a striking crater bears his name. New radar images from the Atacama Large Millimeter Array show for the first time the direct effect of volcanic activity on the atmosphere of Jupiter's moon Io. Io is the most volcanically active moon in our solar system. It hosts more than 400 active volcanoes, spewing out sulfur gases that give Io its yellow, white, orange, red colours when they freeze out on its surface. Although it's 1 billion times thinner than Earth's, Io's atmosphere can teach us about the moon's volcanic activity and provide us a window into the exotic moon's interior and what's happening below its colourful crust. Previous research has shown that Io's atmosphere is dominated by sulfur dioxide gas, ultimately sourced from volcanic activity. However, it's not known which process drives the dynamics in Io's atmosphere. Most likely explanations are either volcanic activity or gas that's sublimated from the icy surface when Io is in sunlight. To distinguish between the different processes that gave rise to Io's atmosphere, a team of astronomers used ALMA to take snapshots of the moon when it passed in and out of Jupiter's shadow. When Io passes into Jupiter's shadow and is out of direct sunlight, it's too cold for sulfur dioxide gas, and it condenses onto Io's surface. During that time, we can only see volcanically sourced sulfur dioxide. So the video shows exactly how much of the atmosphere is impacted by volcanic activity. Today is a milestone in NASA's Perseverance mission to Mars. Last Friday, it had travelled 146 million miles which means the spacecraft is halfway to Mars and its rendezvous with Jezero Crater. So let's take a wee look at Jezero Crater and why NASA chose it as the mission's target. The Perseverance rover has 4 overall objectives. The main 2 are to search for environments that could have supported microbial life in the past, and to search for evidence of that life. The other 2 objectives are to cache samples for later return to Earth by another mission, and to test oxygen production from the Martian atmosphere in anticipation of future human missions to Mars. Jezero Crater was chosen because it can hopefully support the first 2 objectives really well. The crater is a paleo lake, meaning that once it was filled with water. It was probably several hundred meters deep and about 25 miles in diameter. Researchers think it may have filled with water on 2 separate occasions. They also think that Jezero Crater was full for a long time, and that the delta took over 1 million years to form. The lake and the channels that fed it were so long-lived that there may well be up to 1 kilometre. I'm making a right mess of reading my figures, don't it? There may be up to 1 kilometre of sediment on the bottom. When NASA selected Jezero Crater in 2018, the scientific case was strong. It's only grown stronger since then. Along with the preserved sediments and river delta, there are 5 different types of rock the rover can sample. Some of the features at Jezero are estimated to be 3.6 billion years old. That's near the beginning of Mars's Noachian period, which began between 4.1 and 3.6 billion years ago. Noachian is when liquid water flowed over the Martian surface, creating networks of river valleys. Oceans and large lakes may also have been present at this time. Perseverance will be looking for signs of ancient microbial life. It has a suite of powerful science instruments to do just that. It carries a ground-penetrating radar, several different types of spectrometer, and a host of cameras. The rover is really a collection of several robots working together. One of them is the 2-metre-long robotic arm mounted on the front of the Perseverance chassis. It has a rotary percussive drill that can collect core samples for return to Earth. The sample return portion of the mission is complicated and will provide the first samples collected from another planet if all goes well. Perseverance is equipped with 43 sample tubes, and the mission's goal is to collect at least 12 samples. It'll leave the samples in a central location for retrieval by a future ESA mission. And that's the space news for tonight. So back to Alice Amanda.
Right, thank you for that, Roy. That was really interesting. But it was really exciting about the water found in the moon and Clavius crater as well. So, recently. So that was really good. So anyway, right. Tonight we have Dr. John Davis. John is an astronomer at the Royal Observatory in Edinburgh. In 2001, he became project scientist for the European Opticon project, an EC-sponsored activity aimed at integrating all of European astronomers. John is semi-retired, but still works around 3 days a week at the observatory. He also has a minor planet named after him. And the minor planet is 9064. So let's give John our usual warm Kaz welcome.
Righty-ho. Okay, shall I just kick off then, Alice Amanda?
She's muted.
So, no, I'm not.
Yes, just start.
Yeah, okay. I'm not muted according to me. Right, so let me see if I can get this. First of all, hello everyone. I'm sorry I can't be there in person. I think I was scheduled to come in about April, but of course that all went to heck in a handbasket. And so we rescheduled the thing by Zoom. So let's hope it goes okay. So I'm just going to, let me get my brain in gear here. what I've noticed from these Zoom things in the past is that they seem to be, the talks seem to be getting longer and longer. I guess that's because the speakers can't see the audience fidgeting. So I'm going to make a real effort to finish this in the sort of 45, 50-minute slot that we would normally have for a talk if I was physically present with you. So once I get going, I'm going to try and share my screen, and then I'll just do the whole thing on the PowerPoint, and I'll come back on Vision to answer questions at the end. So let's see if I can share the screen. There we go. This one. Now there are next to no movies in this, so I'm hoping we won't have too much problems. There's 1 or 2 GIF files which may just give us some grief, but we'll see. So here we go then. Missions near Earth asteroids. Yeah, as Alice Amanda said, my name is John Davis. I'm an astronomer at the UK Astronomy Technology Centre at the Royal Observatory, Edinburgh. I might say I've been pedaling my way through a 24 lecture series on dark energy and dark matter over the last couple of weeks, which I was given on DVDs. And I can tell you, after 22 lectures of fermions, bosons, dark energy, dark matter, fields, bosons, Higgs bosons, gluons, gravitons, parallel universes, multiverses, vacuum energy, I can tell you I am really glad that I don't do cosmology. So if I can't land on it and it can't land on me, I don't really care. And I'm going to talk about 2 things which could in principle land on me, and which we have already at least touched, if not landed on ourselves. And these are 2 Earth-crossing near-Earth asteroids. So what do we mean by a near-Earth asteroid? In about the 1930s, it had been known since 1801 that there was a population of asteroids in a belt between Mars and Jupiter. But in the 1930s, the first of a group of asteroids which actually crossed the Earth's orbit was discovered. The first one was called Apollo, and these things have been called Apollo asteroids. So these come in 3 flavors. We now know there are many, many, many hundreds of these things. They come in 3 flavors. The ATENs have a semi-major axis of less than 1, so they spend most of their life inside the Earth's orbit. The Apollo asteroids come out of the main belt, cross the orbit of the Earth, and then return to the main asteroid belt. And the Amor asteroids come out of the main belt, cross the orbit of Mars, but they don't cross the orbit of the Earth, and then go back into the main belt. Now, the interesting thing about these things is that their lifetime is only of order 10 million years. So in 10 million years, any of these planet-crossing asteroids will either crash into a planet, be ejected by the sun into some orbit beyond Jupiter, or will crash into the sun itself. So the fact that we see them today means one of 2 things. One, there were gazillions of them a long time ago, and we're seeing the tiny tail end of the population. But it turns out that that's not going to work, because to see the number we see today, there would have to be so many in the early solar system that it's just not realistic. So we're forced to the second conclusion, which is that this population of planet-crossing asteroids is refreshed at roughly the same rate that they're removed. So let's see how that refreshing occurs, because if we look at the asteroid belt itself, this is a diagram in orbital space. So the semi-major axis, the distance from the sun, basically. And what you see if you plot the positions of these asteroids in a semi-major axis is not, as you might expect, a smooth curve, starting with not very many, rising to a big hump in the middle, and then dropping off again. There are distinct gaps in the semi-major axis distribution. This has been known for some time. It was discovered by a guy called Kirkwood, and so they're known as Kirkwood gaps. And the reason these Kirkwood gaps exist is that these gaps occur where the orbit of the asteroid is an exact fraction of the orbit of Jupiter. So the time it takes the asteroid to go around the sun is some fraction, some exact fraction of the time it takes Jupiter to go around the sun. What that means is that every time the asteroid goes round, every few times it goes round, it sees Jupiter in the same place. Jupiter's gravity gives it a little tug, and Jupiter's gravity sweeps these Kirkwood gaps clear of asteroids by partly at least, by throwing them towards the sun. So they become Earth-crossing orbits. So this is the way in which the population of near-Earth asteroids is refreshed. You can't just take an asteroid in the main belt and bash it hard enough to throw it into an Earth-crossing orbit. If you have a collision that energetic, it will actually destroy the asteroid itself. So what you have to have is you have to have objects which are close to these Kirkwood gaps. They have some small collision within the belt. They drift into a Kirkwood gap, and then Jupiter's gravity in short order flicks them towards the Earth. So that's where these things come from. They are main belt asteroids which have wandered into a Kirkwood gap and been flicked towards the Earth into an Earth-crossing orbit. And these new ones arrive at roughly the rate that the existing ones are depleted by collisions with the planets or ejection from the solar system. So this is just background setting for the asteroid population. We'll get on to the near-Earth asteroids in a second. But there's one other concept I want to introduce at this stage, and that's that of asteroid families, because this we'll see why this is important later. This is another one of these diagrams in orbital space, and you see again that the asteroids are not randomly scattered across this diagram. You've got distance from the sun along the bottom, and the orbital inclination up the way, and you see there are distinct clusters within the asteroid population, and these are called asteroid families, and we believe that they are the results of collisions within the asteroid belt. So the Hungaria family, which is in the top left of the screen, is a group of asteroids which all have orbital elements very similar to Hungaria, which is the largest asteroid in the grouping. Then you have all these other families, the Flora family and so on, which are believed to be fragments from an asteroid collision. And we'll see why that matters towards the end. So let's get down to the two particular missions of asteroids, which are both been reaching a climax in the last year or so. The first one I'm going to talk about is the Japanese mission called Hayabusa 2. The clue's in the name. It's a follow-up to the original Hayabusa mission, which was sent to asteroid Itokawa about 15 years ago. Now, the target of Hayabusa 1 was included a sample return from the asteroid. And although they did manage to touch the asteroid, the sampling mechanism failed until they only gathered a very small amount of material. They also had a whole raft of technical problems getting there and getting back. Excuse me. So the plan for Hayabusa 2 was to take the basic Hayabusa design, improve it, fix all the things that are broken the first time, and try again. So the objectives of this mission are multifold: to go to a near-Earth asteroid, go into orbit around it, drop some, we won't call them rovers because they don't really rove, they're really hoppers, little spacecraft which can hop around the surface, to grab one or more samples and bring those samples back to Earth for laboratory study. The target asteroid chosen was this one. I think I pronounce it Ryugu. I have no idea if that's the right pronunciation. It's a C-type asteroid, so it's probably rich in carbon, a bit like a carbonaceous meteorite, probably relatively primitive in the age of the solar system. It's not evolved very much. It's what we call a PHA, so it's a potentially hazardous asteroid. So it's an Apollo, it crosses the orbit of the Earth, and it is in an orbit which makes it potentially an Earth collider at some time in the future. Its size, it's 900 meters in diameter, so it's the size of a decent sized hill. It's less than a kilometer, half a mile or so in diameter. And it rotates in 7.5 hours. And for anyone who cares, the orbital information's there in smaller script. Hayabusa 2 was launched in December of 2014 by a Japanese H2 launch vehicle. This is an indigenous Japanese rocket. This is an entirely, well, apart from a bit of an international collaboration on some of the experiments, this is an entirely Japanese mission. So it was launched by a Japanese rocket from Japan. And like most of these missions these days, it follows a somewhat convoluted path to its target. So it's launched from the Earth, it goes around the sun and then re-encounters the Earth after about a year. The Earth's gravity then flings it further out to bring it into an orbit which is synchronized with the target Ryugu, which was originally called 1999 JU3. That was its temporary designation. So it arrives at Ryugu in July of 2018, and that's when life started to get interesting. So the first thing it does is it parks itself in a distant orbit. Now, the definition of distant when you're talking about these very small objects is actually not very distant at all. So it's 20 kilometers from the center of the asteroid. Remember, the asteroid is half a kilometer in diameter. So it parks itself 20 kilometers away, and it sits there for a while, making detailed images of the asteroid itself. And then occasionally it makes a little foray down to the surface, down towards the surface, to get close-up pictures. So the picture on the left is the whole thing. It's not really round, it's more of a diamond shape. And the picture on the right is a close-up of the surface, and it turns out to be covered in very small, covered in rocks at all scales. This was a bit of a surprise because the thermal models of the asteroid made before the mission took place suggested that it had a low thermal inertia. That is to say, it heats up slowly and it cools down slowly. And that's a characteristic of dusty surfaces, not rocky surfaces. So the expectation was when they got there, this thing would be covered in dust. But it actually turns out to be covered at all scales in stones, which is a potential problem for the sampler. Here's this is an extract from a science paper. It's not important to worry too much about it. I would recommend this document. It's a paper in the magazine Science, which is a very good description of the results from Ryugu. The top picture is the asteroid flattened out in a sort of map projection. It does seem to have quite a large number of impact craters, but I particularly like the little story that goes with this thing in the bottom right here, and that is it's called Ohimi Saxum. It's a large boulder. Now it turns out, because this is such a small object, it turns out that the Japanese wanted to give this thing a name, but there is no naming convention for rocks. There's a naming convention for craters, there's a naming convention for mountains, there's a naming convention for rills, but there's no naming convention for boulders, because how do you decide when you can name something or not? And so there was a bit of kerfuffle that they tried to decide on some rules for how big a boulder had to be before it could have a name. And they eventually picked a value that had to be like 1% of the diameter of the body. And this boulder qualifies, and so this boulder's got a distinct name. The picture B shows two things. One is a ridge which seems to run around the equator. That's the thing marked out by the little yellow dots. There's a circum-equatorial ridge, and then in the blue is a trough, which seems to run down from the equatorial ridge down towards the pole, and that's where this big Ohimi boulder is parked. And the little picture on the right, and let us see, I'm just going to read out, I've got the paper in front of me, I'm just going to read out what it says about this, because I think it's I find it quite amusing. It says, asymmetric regolith deposits on imbricated flat boulders on the northern slope of the circum-equatorial ridge of Ryugu. Small yellow arrows at the edges of the regolith deposits indicate the direction of mass wasting. The large yellow arrow indicates the current geopotential gradient from high to low. The direction of the geopotential gradient is consistent with the mass wasting. Now, I think what all that says is that dust slides downhill. So I think that those entire two sentences can be translated to dust slides downhill. So this is regolith is just crushed up surface material, and it appears to be drifting downhill. But the two main events of this thing are the landers and then the sample grab. So let's talk about the landers first. There were several landers. The first one is called, well, the first ones are called Minerva, and here's a picture of it. This is called Minerva 2-1. It's called Minerva 2 because there was a Minerva 1 on Hayabasa 1, which didn't succeed, unfortunately. And the Minerva 2 experiment comprises 2 different kinds of rovers. This is the type 1, and there are 2 of them. There's also a type 2. So this is Minerva 2 type 1. And these little robots, these little landers, are 18 by 7 centimeters. So they're 18 centimeters across and 7 centimeters high. They're about the size of a sponge cake or a plate. You know, they've got the diameter of a plate and they're about 2.5 inches high. And each one weighs 1 kilometer. And these are simply dropped onto the surface. The gravity of this object is very light because it's so small. And these have vibrators in them, which are not much different from the things that make your mobile phones vibrate. But that's enough to make them jump off the ground and float around for a bit and land somewhere else. So they're not so much rovers because they don't rove, they just hop randomly from place to place. So these were deployed successfully. These are 2 pictures which have come back from these things. Rover 1A lasted for 36 Earth days. That's 113 asteroid revolutions. And Rover 1B lasted for 3 Earth days, which is 10 asteroid revolutions. And between them, they returned some 650 photographs. These are 2 of these photographs. They were the first ones released. But they lack one piece of information which would be really, really useful, and that is they don't have any scale bars. So it's very difficult to know whether you're looking at something which is a handful of pebbles or a handful of boulders here. And believe me, I have tried to get pictures like this with scale bars. I contacted the Japanese Space Agency. I contacted the principal investigator of these landers, because without scale information, it's very hard to understand what you're looking at. But you're looking, what is clear is this thing is completely covered in small rocks. It's absolutely rocky everywhere you look. The second of the landers was this thing called Mascot, the Mobile Asteroid Surface Scout. And this was an experiment produced by the French and the Germans. It's led by the German Space Agency, the DLR, with collaboration from the French. This is a somewhat bigger thing. It's 29 by 29 by 20 centimeters. So it's 2 shoe boxes or a small microwave oven in size. It's that sort of size. It weighs 10 kilograms, 9.5 kilograms. It also has the ability to move, but unlike the first 2 landers, it has no solar panels. It's battery powered, and so it can only be expected to last for a few hours because it just runs off its batteries. It had a 16-hour lifetime. So here it is being released on the 3rd of October. You can see the Mascot in the top of the picture falling towards the surface. It was dropped from an altitude of 51 meters. So that's what, about 160 feet. And it took 6 minutes to fall from the release point at 50 meters down to the surface. And here's a picture of a, quite remarkable series of pictures. Obviously, the picture on the left is expanded on the right. That's the shadow of the mothership Hayabusa. And then when you zoom in, you can see the Mascot spacecraft itself falling and the shadow of Mascot on the surface as it falls towards the surface of the asteroid. This is a picture, again, there's no scale bar. We'll get to some scales in a second. This is a picture taken just a few meters prior to touchdown, and you can see that it's very, very rough. This somewhat cluttered picture I've left in because it kind of explains what's going on with all of this. The Mascot is falling down the yellow line that starts in the bottom right-hand corner of the picture just by the shadow of the satellite. It falls down that line. Photograph D, which is the bottom center picture, is taken before touchdown, looking back the way it's come. And the little white lines, which I hope you can see, mark out the edges of the photograph. So this area here is this area here. It then eventually touches down somewhere over here, at contact point 1, and that's where photograph E is taken. So this is actually taken on the surface. The scale bar is here, 10 meters. Picture C is the same. It's the same picture. It's the same landing site, but it's color coded by height. So it shows the range of height from -3 meters, so 10 feet, to +3 meters, plus 10 feet on compared to some average value. And then the picture in the middle shows what happens while it's on the surface. So it touches down, it bounces a few times. It in fact landed upside down, but it had a spring-loaded arm which could be flicked out, which then flips the thing the right way up. And it can take some size, so it bounces around about here somewhere, over a distance of 17 meters, 50 feet. And then it takes a series of science observations. And then after a while, they command it to hop. So it jumps up in the air and it manages to move itself about 70 centimeters. And they do another series of scientific observations, but both in the daytime, asteroid day and asteroid night. And then finally, just as the mission is ending, they make another couple of small movements on the third asteroid day. Remember, the rotation period is only about 6 hours. So this is about, by the time you get to the third day, you're in 18 hours since the landing. And at last, here's a picture with the scale bar. So this is a picture, here's the scale bar, 5 centimeters. You can see this thing is very rocky. And the infrared experiment samples an area here. And this explains to us why everyone got the surface composition wrong, because it turns out that the thermal properties of this, albeit rocky surface, are very high. It has high thermal inertia, so it takes a while to heat up, it takes a while to cool down again. And you usually get that if the surface is covered in fine dust. But in this case, it seems to be covered more in rocks, which has lots of small gaps in between them. So it's a very loosely aggregated. It's not a solid lump of rock. If it was a solid lump of rock, it would heat up quickly and it would cool down quickly. It's actually a lot of small pulverized rock fragments, and that's why its thermal inertia is low, and that's what fooled people into thinking it was going to be dusty. So then the main event are these 2 sample attempts. The first one takes place in February, about 18 months ago. And the sampling mechanism, which is actually remarkably similar to the one the Americans use, is this thing at the bottom. It sticks out a couple of meters down to the surface. Now, this has got quite large solar panels. This distance is many meters, 6 meters, I think. So this box has to, the satellite has to lower itself down till the sample horn is just touching the surface. And when it touches the surface, it fires a ball bearing into the ground, which in theory kicks up a load of dust and stones, which then bounce around into the sample head and are saved into a little capsule. This thing over here on the left, which looks a bit like Giotto, is actually a little landing marker which was dropped in advance to help guide the spacecraft down. Remember that even though this is in the inner solar system, the light travel time is still several minutes. So you can't fly this thing down with a joystick. It has to be computer controlled. It all has to happen automatically. So as part of the preparations, they dropped this little marker thing to help the onboard navigation system find its way down to the asteroid. Obviously, you've got to get down and touch it. You've got to stay on the surface long enough for the debris to fly up, but you don't want to come down so quickly that you crash. So it's quite a fine trick to get down there and do that. And this is how it looked. This was the first attempt. Here's the landing site before the spacecraft arrives. You can just there's a few rocks here. You might want to try and get a mental picture of these because there's those 3. A few seconds later, after the sample attempt, it's on its way up, and you can clearly see a bunch of disturbed ground here. So let's just look at these 3 rocks again and go back one. Whoops. So there are the 3 rocks here. So this is the area where the landing takes place. And you can clearly see that this is pretty clean. And then shortly afterwards, it's been clearly messed up. So there's every indication that the sampling was successful. But the second phase of the sampling was even more outrageous, actually, because the first attempt gathered dust which had been sitting on the surface of the asteroid for many thousands of or millions of years. And stuff that sits on the surface of asteroids undergoes a process called space weathering. So just as if you have a red car and you park it in the sun for 10 years, and then for some reason you take the wing mirror off, you find that underneath the wing mirror, the red's a slightly different color because the paint has just faded. Well, the same thing happens with asteroid dust. This is called space weathering. It was highly controversial when it was first proposed, but it is now accepted that just exposure to the sun and to cosmic rays gradually changes the color of the surface of an asteroid. So if you want to sample material that hasn't been aged and get really pristine material, you have to go slightly below the surface. And so this was how the Japanese planned to do it. They had a gadget called a small carry-on impactor, which was deployed from the mothership. This is the SCI being deployed. They also deployed a small free-flying camera to photograph what was going on. That's this here. This little thing that looks like a beer can with a pole sticking out the back. And the small carry-on impactor had a explosive shaped charge in it. Now, shaped charge, for those of you who don't speak this language, is the sort of thing you use in a bazooka warhead to blow a hole in a tank armor. It's shaped like a teacup, and it focuses the blast out of the mouth of the teacup. So in this case, the shaped charge fires a lump of metal. All of the blast goes in one direction, and it throws a lump of metal down at the surface, which then crashes into the surface to make a crater. It is important to understand that the explosion occurs in the interceptor. It's not on the surface. The explosion is just to throw a plate of copper down onto the asteroid to make a crater. So the idea is that the spacecraft creeps around the back of the asteroid and hides. You can see it down in the bottom right-hand corner of the picture. Then you trigger the SCI to blow a crater. You use a little camera to film it happening. And then once all the dust has settled, literally, the mothership can creep out from behind the asteroid, and provided the asteroid's not shooting back, it can then go look for the crater that's been created. And there it is. That's the impactor, the SCI, after it's released from the mothership and before it was fired. And this is a picture from a little camera showing that the impactor has in fact worked, because here on the big picture and magnified in the top right-hand corner is the actual plume of material caused when the impactor struck the surface. So that gave the Japanese engineers a lot of confidence that they had indeed fired the thing successfully and created some sort of a crater. They then had to go around and find it. So after waiting for a while for the dust to settle, they set the mothership back around, and after a while they found this crater. And again, there's this rock here, looks a bit like the badge on Captain Kirk's uniform. There it is there. And there's clearly an impact crater here, which wasn't present before. So that's where the impactor landed. Material from beneath the surface has been excavated. This is not subject to the space weathering. So that's the idea, to grab that for the second sample. There's the impact. There's a scale bar down the bottom, 10 meters. You see these things are big, 10 meters, that's 30 feet. This is the size of a big car, a bus, really. But it's very, very rough. And it's quite tricky to get down with those big solar panels, because you don't want to hit a boulder with one of those solar panels while you're attempting your touch and go. This is a picture from the, it's actually a still from a movie, but I haven't put the movie in because I'm terrified of them not working. But you can see the horn, the collector horn, that's that white disc in the center, as the thing goes down, and it fires the bullet to stir up the surface, and then it fires its thrusters to climb away. And this is another still, and you can see there is stuff flying everywhere. So the thruster, the combination of the impact of the probe, the ball bearing that's fired into the surface, and the thrusters to pull it away again, have stirred up a great deal of material. Now there was sufficient resources for 3 attempts, 1 before and 2 after if necessary. But after that, the successfully grabbing a sample before and after successful collection from inside the crater, the Japanese decided not to attempt a 3rd sample grab. I guess because you know, the better is the enemy of the good. They already had 2 samples. They didn't want to risk breaking something trying to grab 1 more sample. So that marked the end of the sampling phase of the mission. And what have we learned from all of this? Well, it turns out that the chemistry of Ryugu seems to be that of aqueous material, rocks that have been altered by aqueous alteration, so by water. But there's no evidence for water there now. So what we think has happened is Ryugu formed as part of, in the top left-hand corner of the picture, you see a large asteroid forms. It's big enough that there can be water chemistry going on. I mean, not water flowing on the surface, but at least chemistry of water inside the rocks. And then one of 2 things happens. Either the asteroid heats up from the inside because it's trapped radioactive material. 26 aluminium is a radioactive material that decays and gives out heat. Or it's hit by a number of small things which individually create heat pulses which soak into the interior of the asteroid. The most likely explanation is in fact that it's formed with enough aluminium 26 in the mother asteroid to heat up the inside and dry it out after the aqueous alteration had taken place. Then something else, another asteroid, crashes into the mother asteroid and wrecks it, blows it up into lots of pieces. And this is where we get back to this idea of asteroid families, because we know from the asteroid families that these catastrophic collisions do occur. So there's an impact. The mother asteroid is disintegrated into large numbers of pieces, which then gradually reform under their own gravity to form another asteroid, which is a rubble pile. So it's a large number of fragments that have aggregated under gravity. And then this, or possibly later on, it's hit again, and the daughter asteroid is smashed up again and forms a granddaughter asteroid as the little bits from that all reaggregate. And that's what we've got today here in the left-hand side of the picture. We've got this asteroid which has been formed, the rocks in it were formed in a much bigger object which was smashed apart, reaggregated, smashed apart again, possibly reaggregated and smashed apart yet again. And that would explain why the surface is so rugged, because what we're looking at is not really a solid body at all. It's just the result of multiple collisions and disintegrations and reaggregations. So that's where we are. That's where we are with the science. The mothership departed the asteroid in November last year, and it's due to return to Earth in December. So not that far away now. The mothership will fly close to the Earth. It will release the return capsule, which is a sort of re-entry vehicle. Looks like a little Apollo capsule, but it's only about the size of an ice bucket, which should be aimed at Australia. The mothership will then make a small maneuver so that it doesn't crash. The mothership will fly past the Earth, and the sample canister will hopefully land in the Woomera missile range in Australia under parachutes in about 2 months now. And that will then be recovered and the asteroid material extracted. The mothership, if all goes well, may still have sufficient fuel to go to another asteroid. One possible target is this one, 2001 WR1. Of course, it can't do any more sampling because it's run out of resources and it's already returned its return capsule, but it could still make a rendezvous and map the thing and take loads of photographs and that sort of thing and do chemistry and spectroscopy from orbit. So we'll see. The original Hayabusa, say, suffered multiple failures during its mission. This one seems to be going a lot better. And with luck, it'll get a chance to visit another asteroid later. So that brings us on to the second mission. this thing called OSIRIS-REx, which has to be the most contrived acronym you can imagine. Origin, Spectral Interpretation, Resource Identification and Security Regolith Explorer. Well, crikey, who thought that up? OSIRIS-REx is one of a NASA series of missions called New Frontiers. They go through these phases where they reinvent programs, where they give them different cost caps and so on. The security aspect of this is a SOP to NASA's instructions from Congress to investigate asteroids which are potential Earth colliders and so could affect life on Earth. Many of you probably know that it's almost certain that the mass extinction of the dinosaurs was caused by an asteroid impact 66 million years ago. Now, what's the difference between us and, why were the dinosaurs wiped out? Well, because they didn't do astronomy. They didn't know anything about potential impacting asteroids. We're a bit cleverer than the dinosaurs. We do know about them. So OSIRIS-REx is tasked with going to a potentially hazardous near-Earth asteroid and exploring it to find out how we might deal with one when we find one that's due to hit the Earth. Its mission very similar to the Japanese mission, but it's mostly sample return. There's no rover element. The target for this one is 101955 Bennu. It's another early type. It's another primitive asteroid, carbon-rich asteroid with an Earth impact, possibly 200 years from now. Most of us probably won't care. It's half the size of Ryugu. It's only 500 meters in diameter, and it spins every 4.5 hours or so. Well, this is a tiny thing. I gave a talk I went to some science event at Dalkeith High School, and I actually I got an aerial photograph of Dalkeith High School and drew the size of the asteroid. It's only just outside the school boundaries. So OSIRIS-REx is launched by an Atlas rocket in 2016. It goes through the same complicated orbital dance as we saw with Hayabusa. It flies away from the Earth. It comes back to the Earth. It gets an Earth gravity assist, which gives it the energy to fly out to rendezvous with Bennu. And it reaches Bennu just around about the new year of 2018-19. So it didn't go into orbit immediately. It made a series of flybys just to get some basic shape information, and it finally nudged itself into orbit on the 31st of December, New Year's Eve, 2018. And this is a really close orbit. Remember, this object is 500 meters in diameter. The orbit is only 1.75 kilometers. So it's only about 3 radii up from the surface of the asteroid itself. And once again, what we see almost immediately, as with the Hayabusa target, is this thing is covered in rocks. There are rocks everywhere. And like Hayabusa, there are 1 or 2 very large rocks. There's one here, and there's one here. I think the next one's just a quick GIF to show the thing rotating. I actually have a 3D model of this. It's about the size of a grapefruit. And if I was physically with you, I would be holding it up right now and twiddling it around in front of me. I'll show it to you at the end. It's just the other side of my curtain. But like Ryugu, this thing is just covered in rocks. It's just completely covered in rocks. The big guy in the middle here is 7.5 meters in diameter, so that's what, 25 feet. And everywhere you look, rock, 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 rock. And this is potentially a major problem, because the planning assumption was that this object would be fairly dusty, fairly smooth. And so the requirements for the landing site were something like a 10-meter diameter smooth piece of terrain. Well, there aren't any 10-meter diameter smooth patches of terrain. They look very hard, and they didn't find any. This is the first all asteroid map. You can see there's rocks everywhere. The naming convention is that most of the things are named after birds. And here again, you have individual stones being given names. So this is the largest one, Ben, and it's 21 meters 70 feet high. Well, this is a big stone, but it's a boulder. It's not a mountain. It's just a boulder. And it's, so you see an impact crater here. These are very distorted, of course, because the object is not even round. It's more of a diamond shape. But the really big surprise was something which turned up in navigation cameras, and that was somebody was taking some pictures to get the star fields in the background for navigation, and they suddenly realized there were lots of stars that shouldn't be there. And what's happening here, and this has been repeated numerous times, is that the asteroid is actually throwing stuff into space. Now, these individual dots here are not stars in the background. They are pebbles, a couple of centimeters in diameter, an inch or so in diameter, which are being ejected from the asteroid itself. Some of them are ejected completely into space. Most of them just do a couple of orbits and then crash back onto the surface. This was a complete surprise. I mean, I was absolutely blown away by this, as indeed were most of the science team on the mission, I'm sure. We know that comets eject material because comets have loads of ice and gas in them, and as the sun warms it up, the ice vaporizes and blows stuff off to form the comet's tail. You expect to see this sort of thing in comets, and we did see it in the pictures from Rosetta. But no one, I don't think anyone, really expected to see stuff being blasted off asteroids. Now, there are several possibilities that were looked into. One is it's impacts from small meteorites just kicking up dust. Another is that it's some sort of trapped volatiles which are being warmed by the sun and then vaporizing and blowing pebbles away. But the most likely explanation is actually to do with the thermal cycling. Almost all of these ejections turn out to occur about 2 in the afternoon local time. So what seems to be happening is the asteroid rotates, the sun shines on it, the rocks heat up very quickly, the individual stones heat up very quickly, and maybe sometimes they shatter and pieces get flung off into space. There's not that many of them. They're quite a long way apart, so they didn't present a threat to the sample capture, but this was a very surprising discovery. And another surprising discovery, it was certainly surprising to me anyway, is that there are a small number of very bright stones on the surface of Bennu, and these are almost certainly pieces of V-type asteroids. Now, V-type asteroids are a favorite of mine because 9064 John Davis is a V-type asteroid. And V-types are fragments of Vesta. So if you go to Vesta, and the Americans have sent a mission to Vesta, Vesta has some huge impact craters which blew away like a big chunk of the southern hemisphere. And so there are a whole cluster of asteroids, a little asteroid family, which all have chemical compositions or spectral signatures very similar to Vesta, and these are called V-type asteroids, V for Vesta. And one characteristic of the V-type asteroid is they are very bright. They have high albedo. They're very reflective. And the chemistry of these things on the surface of Bennu is identical to the chemistry of V-type asteroid. So these would appear to be bits of Vesta, which were exploded off Vesta at some point billions of years ago to form smaller V-type asteroids, and then themselves disintegrated and somehow found their way onto the surface of Bennu. So that's a pretty remarkable discovery as well, I think. So then we get on to the sampling, and of course, if you've been watching the news, you know this has all been going on in the last couple of weeks. So I thought we just investigate this a bit more. Here's the general view of the spacecraft. You don't need to worry about all these funny acronyms like REXIS and SAMCAM and MAPCAM. These are the scientific instruments, cameras, spectrometers, optical, visible infrared, spectrometer, and so on. But the TAGSAM is the so-called touch and go sampler, and that's the trumpet-like thing that's sticking down in the bottom left-hand corner. Just like Hayabusa, the idea is that this thing will gradually take itself down to the surface, touch the surface for a few seconds, but instead of firing a ball bearing into the surface to kick up dust, it squirts a blast of nitrogen gas. And hopefully we'll see how that works in a second. And the nitrogen gas is supposed to stir up the rocks and dust. Remember, there's next to no gravity because the thing is so small. Stirs up the rocks and dust, which are then trapped in the sample head. The sample head is then returned to the mothership, and it's parked inside here. This is the re-entry capsule. So this is the little Apollo capsule that's going to bring the thing back to Earth eventually. For scale, this is what it looks like. Here's someone in a clean room. This is not a COVID mask. This will just be a clean room mask. You can see the size of the sampler. It's a bit bigger than a trumpet, but it's not huge. And it sits on this long arm that projects away from the rest of the spacecraft. Here are some of the potential landing sites. See, I say that they were looking for something which was smooth over 10 meters, and they found it very hard to find such places, but they did find 4 candidates. They've all got names. They're all named after birds, as is the naming convention for this object. And the target chosen is the one in the top left-hand corner, the so-called Nightingale landing site, with the one at the bottom left, Osprey, was the backup. But they did in fact go to Nightingale in the end. You can see how tricky it's going to be to navigate down into getting into that circle without bashing the solar panels against some of these big boulders that are lying very close to the landing sites themselves. Luckily, the performance of the spacecraft's control systems was somewhat better than expected, so they could actually make very precise fly downs, and they made multiple practice attempts before they went for the actual landing. So this is the TAGSAM sampler. I just put a still in here. I've got a movie which I'll show you in a second. Hopefully it'll work. This is the TAGSAM just as it's about to strike the surface to grab the sample, and you can see it's not dusty at all. There might be some dust in there, but it's rocky down to the level that you can see. You saw how big the TAGSAM was in that picture with the gentleman in it. So you know how big it is. It's a bit bigger than a dinner plate, but not much. So you can see that these are stones of all scales in the centimeter to tens of centimeter ranges. And this is the smooth bit. Remember, this is the bit they picked out that was especially smooth. And these are COVID masks. This is the reaction in mission control when they do their first sample grab. Everything seems to be going well. It's a high five all round. So let's see if the GIF works. So here we go. You'll notice that just before touchdown, the tag sample itself makes a little kink to make sure it hits, there it goes, to make sure it hits dead flat. And then it stirs up a load of stuff, both from the impact, from the nitrogen gas that's blasted down to stir up the dust, and then from the thrusters firing as it backs away again. Now, I grew up with the Apollo program, and the idea you could get photographs of this quality in near real time on an asteroid is just fantastic, isn't it? But although everyone was absolutely chuffed to bits at first, everything seemed to go absolutely swimmingly, they immediately discovered, well, they very quickly discovered that they had a problem, and that was that material was leaking out of the sampler. Now, I had to spend a bit of time trying to figure out what was going on here, because you may have heard the stories about a flap not closing. The original plan, and it shows you how clever engineers are, was that they would spin the spacecraft with the arm extended and measure how it reacted. Then they would do their sample grab, and they would spin it again. And because the sampler would now be full of dust, it would weigh slightly different, so the inertia of the spacecraft will be different, so the spin would be different, and from that they could work out how much stuff they'd got. And if it wasn't enough, they had enough gas for 2 more attempts. What they found as soon as they looked at it was, this is just the same 3 pictures repeating, that stuff was actually drifting out. Dust was actually drifting out of the sampler. It seems that they got so much stuff that some small pebbles had got jammed in it and were stopping the door, the flaps closing, and so stuff was leaking out again. So they abandoned this attempt to respin the spacecraft in case they flung the dust out by accident. And what I hope to show now is how this thing is supposed to work. So here we go. Here's the tag SAM. It hits. Here's the cutaway. There's the nitrogen gas blasting down to extract material. The material flies up and it pushes aside these two red flaps, and then it blows itself into the sample container. So what seems to have happened is they stirred up so much material that these two red flaps here opened okay, but they didn't close because this area here must have been full of little stones and pebbles, and that's why they decided not to do any more spinning, but to try and grab the sample which they'd got before it leaked away. So the next thing they have to do is to get the sample back into the mothership, and this is how they do that. So there's the return capsule, this thing in yellowy gold down the bottom. It opens up. Here's the tag SAM with the sample head here. Now remember, the dust is trapped here in the sampler, and they very carefully use the arm as a little crane, if you like, to lower the sample head into the re-entry vehicle where it latches. Then they disconnect it here, move the arm out of the way, and this lid closes to seal the thing up. So then they have, say, like a little Apollo capsule ready for Earth re-entry. And that's what they're doing at the minute. This is one of the things that is not done fully automatically. It's done by a series of individual commands, and they have to stop and check after making each move to see where they've got to. I guess they've probably got it closed by now. I don't actually know. Again, they can't just joystick it because the light travel time is too long. They have to make discrete steps, check in every step along the way until they're satisfied. There was enough nitrogen gas for 3 attempts, but they were so satisfied that they'd got more than enough on the first attempt that they decided not to try it again. So the plan now is that the tag SAM sample will be locked into the re-entry vehicle, and they wait until March when the return window opens. So that's when the Earth and the asteroid line up in such a way that the spacecraft can start back to Earth. So it shoves off from Bennu in March. Takes about 2 and a bit years to get back, so it should be back in September 2023. And the process is pretty much the same as with Hayabusa. The whole spacecraft is aimed at the Earth. The sample return canister, that's what the SRC stands for, that little ice bucket-sized Apollo capsule, is disconnected from the spacecraft and aimed at the Earth. The spacecraft then fires its thrusters to move itself away from the Earth so that it doesn't crash on the Earth. And who knows, if they're lucky and they've got some fuel left, they may then send it off to some other asteroid. The sample return canister hurtles through the atmosphere till a parachute comes out, and then hopefully, if all goes well, the capsule lands in the Utah desert in September of 2023. So that's what, 3 years from now. And that's the end. I think I've achieved my objective of being under an hour. I do have a few more slides if anybody really wants to see them, but I thought at that point I'd just stop the share and appear to you so I can try and answer questions. Stop share, there it is. Let me get my toy.
Amanda, you taking over?
So here is my model of Bennu.
All right, right.
If I was with you, I'd be passing this around so you could all have a look at it. And it's
Right.
just for comparison. This is the Churyumov-Gerasimenko, the nucleus of the comet that Rosetta went to. Not necessarily at the same scale.
Aye, right.
3D printing is a great tool for this sort of thing. And this one, you can actually see one of these. Well, you might be able to see anyway. One of these big boulders is right
Aye.
here.
Mm-hmm. Aye, because a lot of the rocks that you seen on both the asteroids, they look quite angular.
Yeah, because it's big. Because they're. Oh yeah, that was one thing I meant to say but didn't. In fact, both of the both Bennu and Ryugu look as if they could be members of the same family. You remember?
All right, okay.
Remember you said at the beginning that asteroids, disintegrated asteroids, seem to cluster in families. There are two families,
Aye.
both of which are good models for both Ryugu and I'm just trying to look for the names of them. I got them written down somewhere, but I've forgotten them now. So that's they both seem to have gone through this multiple smash up, reaggregate, smash
Aye.
up. Well, it's not surprising that they're covered in bits and pieces.
Aye. Right, is anybody got any questions?
Yeah, I was going to ask, are these asteroids, are they complete aggregates, or is there a larger chunk hidden inside?
Mostly, I would think, I mean, bearing in mind these things are only a few hundred meters in diameter to start with, I would say that they don't have a core as such.
Mm-hmm.
They are just literally rubble piles or whatever. Some people don't like the word rubble pile because it implies that they were a house once and then they've been knocked down.
All right.
Yeah.
But they are loose gravitationally bound aggregates. Seems to be the explanation. I mean, bigger asteroids have proper cores, for sure. That's why we get nickel iron meteorites, because the big asteroids, you know, they differentiate. The iron sinks to the center, and then they get smashed up. And bits of crust go one way, and bits of core go the other way. But these things are almost certainly rubble piles.
Thank you.
Yeah, that's the question I was going to ask as well, because remember in the science fiction films up until about 10 years ago, it was always flying into space and then mining an asteroid and building habitats, etc. But whenever we get up close to asteroids now, you know, it looks like they are just rubble piles, as you say.
Yeah,
when you're saying the bigger the iron ones, how did we know that? Is that through tracking the orbit to know they're solid, or is it some other reading you can take?
Well, if you look at the meteorites in our collection, first of all, you don't see many carbonaceous because they're very fragile. That's one of the things that the mascot showed, that these carbonaceous materials are very fragile, have lots of holes in them, so they don't survive entry. But the stony meteorites and the iron meteorites are strong enough to survive re-entry and be picked up and stuck into museums. So the explanation for this is you have a big asteroid, so OSIRIS kind of size, several hundred kilometers in diameter. They have enough radioactive material trapped inside to get hot. The heavy stuff sinks to the middle, forms an iron core, and then at some point in the future, they get impacted and disintegrated. And so you get bits of iron going one way and bits of core, bits of crust going the other way. Most meteorites, the orbits of most meteorites are not tracked. I mean, it's becoming easier because more and more people have digital cameras. So you can set up fireball tracking networks. But until everyone could stick a digital camera in their back garden and go to sleep, the actual orbits of most meteorite falls were unknown.
Okay.
In fact, if you haven't had it already, there's a chap at Glasgow who does an excellent talk about tracking meteorites from tracking networks.
Thank you.
All right, okay.
I'll put a couple of comments in the chat. One, I think there's a movie somewhere that shows the sample return container actually closing on someone's Twitter account. So it looks as though that was okay. And the other interesting thing is that they said that the sampling head actually penetrated something like 19 inches into the surface of the asteroid, apparently. So it's obviously relatively soft.
Yeah, well, if it's unaggregated, if it's just an aggregate of stones, I could imagine that if you push hard, you might well push right away into it.
Well, I'll say the arm would, if you tried that on Earth and tried to bury it on Earth to 19 inches, I think the arm would bend, wouldn't it?
Yes, I'm sure it would.
Strong.
I'm sure.
And I think the spacecraft weighs, it's quite heavy, isn't it?
I can't remember. But I mean,
so it had a fair amount of inertia to stop.
Yeah, it's not. I mean, it's not a small thing. If you saw the picture of the beginning, where there's a
Yes.
couple of blokes standing next to it, you're clearly looking at something the size of a small car. You're not looking at a box. You're
No,
not
no, I
looking
think
at
it's a few
fridge.
tons or something, a couple of tons or something. I can't remember.
Probably.
But
I don't have
it's a
that
fair
number.
amount of inertia, even though it's only moving very slowly.
Right, because Kathy says, "Hi John, you say these asteroids are more or less medium risk of Earth impact. Do we know currently of any that are high risk?"
No, is the simple answer. When people realised that the dinosaurs were probably crocked by an asteroid impact, there was some kerfuffling in Congress, and NASA were tasked with identifying every potentially hazardous asteroid of a kilometre or larger. And then when they'd done that, they were then retasked with doing the same job down to a few hundred meters. And right now, we don't know of anything likely to strike, anything of any size likely to strike the Earth in the next 100 years.
Right.
Now, that's not to say that there might be some that we haven't found,
Aye.
but they think that these big surveys have identified something like 95, 97% of the potential Earth impactors, and none of them are likely to strike the Earth in the next 100 years. So there's the odd chance of a random background event. I just to say, one of the 3% we haven't managed to find yet, but it's not very likely. The asteroid astronomers have come up with this thing called a Torino scale, which runs from like 1 to 9, where 1 is an impact big enough to upset a few people, let's say, and 9 is enough to wipe out all life on Earth. And so far, nothing's got even close to a 2. There's been a few 1s where the probability of an impact is not 0, and the consequences are not too good. But a 9 is a dead cert hit of something big enough to wipe out everybody on Earth. And so far, they've never got the Torino scale above about 1. And they've almost always gone away when the orbit's been refined and the impact probability has been reduced to less than 1%. There's this thing 99942, Apophis, which was fairly high for a while because it looked as if it might be on an Earth impact trajectory in 2020s. But I think that risk's gone away now as well.
Right. So nothing like in the movie Armageddon.
No, not at all. And
so we're deep impact, so we're all right.
yeah, I mean, one of the things which has come about, particularly from the results from Hayabusa 1 and Hayabusa 2, and now from OSIRIS-REx, is that actually throwing an atom bomb at these things is probably the worst thing you can do.
Aye.
Because you can't deflect it because it's not a solid thing. All you do is you convert a bullet into a shotgun blast, and it's not clear which of those two things will be the most dangerous, actually.
There have been 1 or 2 asteroids coming between the Earth and the Moon in the recent years, I remember, where they weren't known about until they had actually gone through. Or they were
Indeed so. Indeed so. In fact, I mean, I wrote something. I mean, I wrote about this in the 1980s. I wrote a book about this in the 1980s, and that was one of the things I said was that, an asteroid approaching from the sunlight side of the Earth, it will be daytime, and so no ground-based telescope is going to see it, and it will just come like a bolt from the blue because it will literally be that. And that's exactly what happened in the Russian meteor strike a couple of years ago, wasn't it? I mean, this thing just appeared in the daylight sky without any warning, and then exploded and blew out the windows all over the place. And everyone who was hurt by flying glass rather than by bits of flying meteorite.
Yes, due to the sonic bang. And of course, there was the one in 1908, as thereabouts, that flattened forests in Russia.
Aye, Tunguska.
Yeah, the Tunguska was a bit bigger. That's probably, I mean, I don't know what the current size estimates for that are, but that was 100 meters.
Mm-hmm.
But the thing that exploded over Russia recently was what, 5 meters or something? Force might know. Do you know how big it was? No, it wasn't that big.
How big was the one that hit Meteor Crater? Was that about 100 meters? Or?
Yeah, I think that's right. And possibly a little bit smaller than that because it was an iron meteorite.
Yeah.
We know it was an iron because the whole area around the crater is full of iron meteorites. And in fact, I go a bit off topic here, but Mr. Barringer bought the mining right. Mr. Barringer realized that this was a meteorite crater and guessed that it might be a nickel iron meteorite. And he bought the mining rights to mine the crater, thinking that he would find a big lump of nickel at the bottom of it.
Mm.
And after spending many years digging and drilling and so on, he never found anything. And we know now the reason is that when the thing strikes, it vaporizes. And so all of the nickel iron, there's no big lump at the bottom of the crater. It's all blasted out, vaporized in dust. And all of the bits that you find around the outside of the crater are mostly bits that fell off just before it hit.
Ah, right, okay.
I actually got a letter from Mr. Barringer's grandson, because I call it the Barringer crater, and lots of people just call it Meteor Crater. And he said how pleased he was to see that some astronomer, at least, was taking his grandfather's name for the crater. Kuhn Butt, I think it was originally called. Kuhn Butt.
Right.
How does this view of the sort of flying gravel pile affect the sort of ideas about the risk profile of these objects now? Because you talked about a number of mechanisms that might spoil material off the surface, but I imagine that one of them might be tidal forces as they come close to a larger object like the Earth or another planet. But what you'd get is just lots of bits flying at you instead of one large piece. So is that changing ideas about risk?
Well, that's a good question, and truthfully, I don't know the answer. I suspect by the time it got close enough to the Earth to be disrupted by the Earth's gravity, it's probably going to hit you anyway. But yes. I think the idea of that's why these sort of Armageddon impact films don't really work anymore, because it does look as if you can't deflect these things by simply hitting them with an atom bomb, because they don't act like a solid rock and move. They would just disintegrate. Mm-hmm. There's another asteroid deflection. There's a couple of other asteroid deflection experiments that are being talked about or being prepared now. European Space Agency has one called Don Quixote, which again is an attempt to see how easy it is to change the course of an asteroid. Because the sooner you do it, the easier it is. If you do it 20 years in advance, you're going to have to change its velocity by a few centimeters per second. And it's job done. Whereas if you wait till the last minute, you've really got to make a big change.
Right.
Can I add, it's Charlie here, just no video, not put videos on the blink, but just a question about what would be the smallest size of asteroid that would have enough gravity to retain those rocks?
Oh, I don't know. I don't know.
That's a silly question.
There was, I seem to remember the asteroid, I've forgotten its name now, that flew into Jupiter a few years ago. We got many pictures of it. It broke up as it came in.
That was Shoemaker-Levy 9.
Aye.
Yeah, and it broke into many parts. There's pictures of all the bits flying towards Jupiter.
Yeah, but it was disrupted on one flyby. I mean, it flew by Jupiter, it was disrupted, and then came around and then back in again. It didn't disintegrate on the way in. I mean, not in the few seconds, not in the few days before impact. It had already disintegrated during.
But if it is like just compacted rubble, you can imagine that would happen much more easily than if it was a solid rock.
Mm-hmm.
Yeah. I'm sure that's true.
What I was particularly impressed by, and you mentioned it, was the quality of the photographs taken when the lander was hovering over the asteroid. You know, they're quite compared to Apollo.
Yeah. Oh, I mean, it's terrific.
Yeah.
Oh, I know.
I did have a few more in originally, and I just took them out because I just thought it was going to start turning into. And here's a really interesting rock, and here's a picture of another really interesting rock. But yeah, I mean, they've mapped the whole of these. I mean, they've mapped the whole surface of these asteroids at a sort of scale of a couple of centimeters or a couple of millimeters. Better than we've mapped the Earth, actually.
But I mean, these images wouldn't be there at the time it was doing that. They'd be received later, wouldn't they?
Yes, that's correct.
Yeah.
But a light travel time, well, it depends, of course, it depends on how, you know, the relative position of the Earth and the Earth and the asteroid at the time. But I think the light travel time is typically 10 minutes or 15 minutes or something.
I see. Yeah.
So yeah, you have to do the, you know, the thing has to do its stuff, and then the pictures come back the next day.
Aye, because the clarity of the images were really spectacular.
Yeah, it's you know, it's fantastic.
Aye.
It's just
Because
technology. I mean, it's just technology, isn't it? We've got
Aye.
CCD cameras these days, and of course, there's no atmosphere to mess the pictures up. But yeah, I mean, I'm astonished. I mean, you know, I don't want to sort of go into old duffer mode here, but you know, I used to study near-Earth asteroids when they were 1 pixel. You know,
All right.
either in the slit or not. And nowadays, you've got these things where you've got individual, almost literally individual dust grains, individual pebbles. You can count them, and it's just astonishing.
Aye, it's phenomenal because I mean that's how I could see that some of a lot of the rocks were angular, you know, because it was so clear, the image. Any other questions?
I mean, surely, I mean, if you're interested in this stuff, I mean, I didn't, but I started making up a list of websites, and I thought, well, this is silly. All you got to do is Google OSIRIS-REx.
Aye.
Or Google Hayabusa. OSIRIS-REx has an excellent website which has lots of the press releases, and with each press release is 2 or 3 photographs that you could download at any degree of, you know, 10 megapixels, 5 megapixels, 60 megapixels, depending how much time you've got. And you can just download all these pictures for free. It's just fabulous.
Yeah.
Right.
Yep. Fabulous.
Right. Any other questions?
Nope.
Okay.
No other questions? Right. So, thanks very much for that excellent presentation. It was really fascinating, you know, learning all about these missions that have occurred that you just sort of heard about now and again, but you didn't know, you know, all the science that they did. You know, you would maybe catch a bit maybe on the internet, why this, but that was really fascinating. I really enjoyed that. Right, so I'd like us to thank John in the usual way.
Thank you.